So, welcome to problem solving session for the course Introduction for the course Linear Algebra. I'm Siddhi Balgambore from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 1, that is, problems related to introduction to algebraic structures like rings and fields, definition and example of vector spaces, and some definition and example of subspaces. So let us start with our first question. So this problem solving session is to clarify your doubts from the lectures and also to solve problems which will help you to understand the concepts taught in the lectures in better way. So if you have any doubts, please feel free to ask the questions. And if you are not here and if you want to discuss any questions, discussion forum is always there. You can put your questions there uh, whenever you want. Okay, and we will try to give the answers as quickly and as much as possible. So let us start with the first question for today's session. So for a comma b in R, uh, let f a comma b from R to R be the function defined by f of ab of x is equal to ax plus b, where x is in R. Then this new set AFF1 comma R is the set of all such functions FAB such that A and B are from R and A non-zero. Okay, and with so this set with operation composition, this set with composition as binary operation is not a commutative group. So we have to check this statement that this AF1R, so let us just set notation here that this, let G be this AF1R just for convenience. And this group AFF1 comma R is called the affine group of R, and its elements are called the affine linear maps. Okay, so this is just extra information which is given. So see here, when they are writing this statement that this is affine, this group here, they have already said that this is group. So we have to prove that this is group but not a commutative group. So for this given set, we need to check that first of all it is a group, and then we will check that it is not a commutative group. Okay, so for group we need to have 4 properties satisfied, and if you're starting with the binary operation, then 3. So that it must be first it must be closed under the given operation. Second, that that operation must satisfy the associativity property, associative property. Third, that there must exist an unique identity element such that under operation, let us call it star, such that identity element is such that A star E for all A okay, and for all A in G. And fourth is that inverse exists and it is unique. Inverse of every element in G has inverse and it is unique. So these are properties of group which we need to check first whether it is satisfied by this set AFF1R, that's affine group of R, and then we will see whether it's commutative or not. Okay, so first property, that is closure property, that we have to check that if an A1 and f A1 B1 and f A2 B2, if this belong to this set AFF1R, this affine group of R, then we have to check that under composition. So my operation is composition. So this AF1B1 composed with AF2B2, FA2B2 belongs to this affine group of R. Okay, and so what this FA1B1 composed FA2B2 is. So this is what FA1B1 applied on this FA2B2. So what is FA2B2? It is A2X plus B2, right? That's how we have defined this set. This FA1X plus B, right? F of A comma Bx is FA1XB. So that's what we are calculating here. So this applied on X is what we are calculating here. So once I have this, then I am applying this function on this new element in R. So note that this belongs to R. So I can apply this FA1 comma B1 on this element of R, and it then becomes A1 A2X plus B2 plus B1. That's how it is defined, right? This is my X now, and I'm applying this function FA1 B1 to this A2X plus B2. And now it becomes A1 A2X plus A1 B2 plus B1. So we have to check whether this belongs to my set A, this affine group of R or not. So note that this anyway belongs to R. So these are just numbers, real numbers, and it belongs to R. So that's not a problem. But now we have to check whether this belongs to R or not. And it has to be non-zero, right? That's how it is defined. This AF1R. So FA comma B could be defined for, we can define it for any A and B from, yeah, any A and, okay, affine group is not abelian. The way we have defined here, it's, yes, I mean, this not a commutative group. So the question is that whether affine group is non-abelian. So that's what we have to prove here, that it is not abelian, that is, it is not commutative group. So when we say something is commutative group here, it means we are talking about whether it's abelian or not. Okay, so yes, it is non-abelian group, and that's what we are going to prove it. That's what we are going to prove. So yeah, so what I was saying that when we defined this FAB, this A and B were from R. We did not have any end condition on R, A and B when we defined FAB. But when we chose elements from this FA comma B, then we wanted this A to be non-zero here. Okay, and in order to say that this element, whether it belongs to this AFF1R or not, what I need to check is whether this A1, A2 is non-zero or not. But note that we chose this FA1, B1 and this FA2, B2 both from this affine group. Okay, this affine 1R. So this implies that A1 is non-zero and A2 is non-zero. So this A1, A2, the product must be non-zero. So that's why this function, this new function which we obtain, this FA1, B1 composed with FA2, B2, which is apparently F. If I try to write this in terms of the given expression, this is F A1, A2, comma, this A1, B2 plus B1. This definitely belongs to F of 1R because since A1, A2 is non-zero, since A1 is non-zero and A2 is non-zero. So yes, this composition on this set affine group on R is just a second, is binary operation. Okay, it satisfies the closure property. And now second is associativity. We have to check the associativity of this. Sorry for that. Associativity of this operation. So what we need to check in that case, to check F A1 B1 composed with F A2 B2 composed with F A3 B3, whether this is equal to F A1 B1 composed with this F A2 B2 composed with F A3 B3. So note that these are very routine, what I can say, routine checks which we are doing here, but these are also really important to understand because when we try to actually check something and try to prove it, we understand the uh, details which we often neglect when we assume some things. So let us start with this LHS. What? So that is F A1 B1 composed with F A2 B2 composed with F A3 B3. So what is F A1 B1 composed with F A2 B2? So it has something like this expression. In fact, it is the expression. So it is F A1 into A2, A1 A2, comma this A1 B2 plus B1, right? A1 B2 plus B1 composed with this F A3 B3. So instead of writing this F A3 B3 and I'm applying this directly on X, so this now becomes A3X plus B3. So this is A1 A2 A3X plus B3 plus A1 B2 plus B1. And when I simplify this, it becomes A1 A2 A3X plus A1 A2 B3 plus A1 B2 plus B1. Okay, and now I have to check the other side, that is this expression, whether it is equal to this or not. So let us calculate that one, that FA1 B1 composed with FA2 B2 composed with FA3 B3. I hope I am audible and still visible to you all. applied on X. So this is B1 applied on this F. We saw that what it is. It is, okay, so let me just write it. It is A2, A3, comma, A2, B3 plus B3. Okay, if you check, this is how it looks. It must be B2 here, yeah. Applied on X. So this becomes F A1, B1 applied on A2, A3, X plus A2, B3 plus B2. So this is A1, A2, A3, X plus A2, B3 plus B2 plus B1, and it becomes A1, A2, A3X plus A1, A2, B3 plus A1, B2 plus B1. And you can check that these two are exactly the same expression which we got. So you can check A1, A2, A3X and this A1, A2, B3, this A1, B2, B1, A1, B2, B1. Okay, so therefore I have this left and right hand side equal, so it satisfies the associativity. So far we got that it satisfies the closure, it satisfies the associativity, and now we have to check the identity element. So what is the identity element? So all are good. So identity, so what is your guess for identity element of this composition operation on my, so we are already calling it affine group. We are yet to prove that it's a group, but yeah, this set AF1, AFF1R. What is your guess for the identity element? So what is identity element? So identity element, so what I need to have is, I need some function f from this set such that whenever I compose this f with any, we need such that for all f a1 b1 in this AFF1R, I have f composed with this f a1 b1 to be equal to f a1 b1. So what is your guess for that? Or instead of a1 b1, let me just take ab. Does not matter. Well, so what when I say what is your guess for that, I mean what is, so my f will be of the form sub a f ax plus b. So what I need to choose a and what must be b such that this f composed, no, let me just take cx plus d. So what must be my c and d such that f composed a comma b must be equal to f a comma b? Any guesses for this? Uh, One is what? Are you saying that the f is just function 1, or you are saying c is 1 or d is 1? What's your guess? Because if you're saying f is just function 1, then observe that this does not belong to my set, this AFF1R, because what is, because when I write f as ax plus b, then it is 0x plus 1, and I need a to be non-zero for f to belong here. So in normal multiplication of functions, this constant one function often work as my identity of a group. So if I am looking at all the functions which take non-zero values under multiplication, pointwise multiplication. In that case, that would work. But here it's different. We are talking about composition function. So what is the guess? Or you wanted to say something? Anyone? So what I think Pragya was suggesting that she wanted to choose f to be equal to maybe c is equal to 1. So this f maybe x plus 0. So how to go to this is I will just take this f a comma b and I compose this with f a, c comma d and compose with, then it is what, as c a comma cb plus d, if I am correct. That's how we are doing this, right? Yes, cb plus d. So I want what, this ca, I want this to be equal to f a comma b, right? So then my ca must be equal to a. So this c becomes, we want this is equal to this, and I want this, I want this. Let me write this. This implies I want ca to be a. So then c becomes 1. And once I have 1, then what I want is d to be equal to cb plus d. So this will imply, wait, if I compose this cax plus b plus d, so this is cax plus cb plus d. Okay, yeah. So I want b, yes, here it is b, right? So I want this cb plus d to be equal to b. So c, we already got it is 1. So I want b plus d is equal to b. So I get d to be 0. Okay, so therefore, by the calculation which we did, I want that function, I get that function f, which I wanted as identity, as x plus 0, that is just x. So this is 1x plus 0, that is just x. And if we check now, this f composed with this f a comma b for any function, this is f composed with ax plus b, but that is what? 1 into ax plus b plus 0, and that's my ax plus b. So therefore, this f is equal to f1 comma 0, that is just identity function on R to R. When I say identity function, it's different from the identity of this group. Identity function, I mean x mapping to x function of from R to R, actually gives us identity of this affine one group, or affine group of R. Okay, I hope this was clear. So now I need to check the inverse. Note that whenever we talk about group, once I have the binary operation, I can talk about its associativity. But I mean the closure and its associativity. Uh, but in order to talk about inverse of some set, whether it forms group or not under that operation, given operation, I first need to have the existence of identity. Without identity, we can't talk about inverse. Okay, so whenever you are talking about inverse, we must have identity. Otherwise, it does not make any sense to talk about inverse. And when identity exists, it is unique. Uh, uh, And when we say something is a group, then if the inverse exists, then that inverse is unique. But in general, there are operations where we can have all the, I mean, it's closed, it could be associative. Um, Identity exists, unique identity exists, but inverse need not be unique. Okay, so to declare something to be group, we must have identity unique, yes, but we must also have inverse to be unique as well. Okay, these are few, what I can say, um, things which we should notice when we learn the definitions, that when we talk about inverses, it must be unique and stuff. Okay, so yes, so now we have to talk, we need to find, yeah, inverse of this. So what I want is, so I want for given f a comma b in this set, we need to find f c comma d in this set again, such that f a comma b composed with f c comma d. I want this to be f1 comma 0, right? That's what having inverse means. Okay, so let us just calculate how we did for the earlier case. So we will just simplify this f a b of cx plus d. I want this to be equal to x. So that is a c. I want to find this, okay? I need to find cd. So let me just highlight this, that we are trying to find this fcd. So this a cx plus d plus, let me just write this. Consider plus b, and this is acx plus ad plus b, and we want that acx plus ad plus b to be equal to x. So this implies this ac must be equal to 1 and ad plus b must be 0. So ac equals 1, this imply this 1 must be, c must be 1 divided by a. And note that this is well defined, because when I choose my FAB from affine group of R, this A is non-zero. So this C being 1 by A completely makes sense. Okay, and now this second thing, AD plus B is equal to 0. I want to find D. So this imply that AD is equal to minus B, and then D becomes minus B by A. And again, this is well defined because A is non-zero. Okay, so the inverse of this function is, so I get this C comma D, which is my F A comma B inverse, is F of minus, what was C? C is F of 1 by A comma minus B by D. Sorry, B by A. This is A. And let us check whether this inverse is, if we calculate it correctly or not. Okay, so this f of 1 f of a comma b composed with f of 1 by a comma minus b by a, what this will be? This will be f of a comma b 1 by ax plus minus b by a. This is a into 1 by ax my plus b by a. plus minus, sorry. So this is x minus b plus b, and I get what? Yeah, x, which is my identity of which we obtained in earlier, which we saw that it is identity of my group. So, I mean, identity of this set. So I get that for all, and this is unique. I mean, the way we have calculated it, it has to be unique because that's how, yeah. Because the moment I fix this, if I choose one element f a comma b from my set, this d which I obtained here, the c which I obtained here, it is fixed. I mean, c has to be 1 by a, otherwise I won't be getting here x. Okay, and the secondly, this d I need to be 0. Sorry, this constant function here needs to be 0, and that's how this ad plus b must be 0. And the moment I fix this f a comma b, this d here also get fixed. So this, by the very calculation or the way we have constructed this inverse of my element f a comma b, I get that it is unique. Okay, because it depends on the a and b which we started with. Okay, any doubts here? So that's how we get that for all a comma b in this set f1 comma r, we get the element. I know that this belongs to my affine set 1 comma r. Okay, affine group 1, because this, since this a non-zero, this 1 by a is non-zero. Okay, so the element f1 by a comma minus b by a is the inverse of f a comma b. Okay, any doubts here? The way we checked everything. So this is what we um so far we just checked this, that this is a group. Okay, now we have to check whether it's a commutative group or not. So what we need to check, so the commutativity, or as Pragya said, that whether it's or abelian property. So what we need to check, that if I choose for f a1 b1 comma f a2 b2, if they belong to my set f1 comma r, we have to check whether f a1 b1 composed with f a2 b2, whether it's equal to f a2 b2 composed with f a1 b1 or not. The moment I have this, so I have to check this whether it's true or not. So let us start with my first f a1 b1 composed with f a2 b2. And what it is a1 into, I'm directly writing the expression a2x plus b2 plus b1, and it is what? This is a1 a2 x plus a1 b2 plus b1. And when I change the order of a2 b2 composed with f a1 b1, it is what? a2 a1x plus b1 plus b2. And the moment I write this, I can see that this is anyway not equal. So this a2 a1x plus a2 b1 plus b2, they are not equal. So this two things here, let me use these two things here, they are not equal. Okay, and so therefore composition, let me write composition is not a commutative operation on AFF on the group this AFM. I can write this now 1 comma R. So we check how can we think? How can we think? How? Oh, what was the question? Could you please uh, explicitly ask me that how can we think? What I mean, the thought process about. Okay, clear. Okay. Uh, please. If I miss reading your message in the chat, you can just unmute yourself and ask the question, and I'll try to answer that. Okay. Um yeah. But I hope this one was clear. That how we showed that this group, how whether that yeah, how we calculated the inverse and everything. Okay, so this is more or less how we check whether the given set forms a group or not, and that's what you can check to. I mean, whatever the questions you are getting in the assignments, or if you are giving exam in the exam, that's how you have to check. Uh, these four properties and to calculate inverse. So for example, here when we try to find the inverse, it exists. I mean, we could find it. Okay, if we did not have that condition that if when I choose from this set ff1 comma r, if this f was just ax plus b for any a comma b in r, and this if this condition that a is non-zero, if it was not there, then I don't think we that would form a group, because inverse would not exist in that case, because does not matter whatever my identity, if at all identity exists. I mean, this x itself would work as an identity, that's not a problem here, but yeah, it would work as an identity, but inverse won't exist because I want this C. I mean, we calculated that C needs to be 1 by A in order for inverse to exist. And if A was not 0, this C, it won't make any sense. And that's how we will get that it won't form group if we don't have this specific condition in order to define this set, a fine group of R. I hope that is clear. And I mean, we should move forward to next question. So I hope it was clear. If not, please ask, or I will just move to next question. So these are some notations or setup, we can say that this n is set of all natural number, which, so if you like look back in the school, we used to call the set one. I mean, let me just write that the set 1, 2, 3 as natural numbers, and this set 0, 1, 2 we often used to call as whole numbers, but in the course, Professor Patil already considered that whenever we will talk about natural numbers, we will include 0 in that, and this z will be plus minus n, such that this n is in natural number. So when I write this here, it also includes 0. Okay. So when you are solving questions in assignment, or if you are giving exam in the exam, please understand that n includes 0. That's how we are we are setting the notation for the course. So don't miss out on 0, because 0 of most of the cases works as counter example, if at all it has to. I mean, the given question or statement needs counter example. So don't miss on that. And next notation is this n plus. which is also z plus. So that is now my n, which the school we used to call natural numbers. Okay, this n greater than equal to 1. So now we will see the few questions that let yeah let star be a binary operation. So when we say something is a binary operation, the closure is already there. So we don't have to check for closure property. When someone says that let star be a operation, we define this operation star on x on some set uh, like this. And if we are asked to check whether the set is forming group under that operation, then we have to check the closure property. And that's how we will get that the given operation is binary operation. But here they have said that star is a binary operation, so we do not need to check that it satisfies the closure property. Okay, so we have to check that this star is a binary operation on the set of integers z plus. This is all those n in n such that n is greater than equal to 1, defined by n star m z plus n comma n is GCD of m comma n, that is greatest common divisor of m and n. Does not matter, GCD of m and n. Okay, and we have to prove that star is associative operation, and also discuss the identity and inverse of this operation on z plus. So we have to check the associativity property. We have to prove the associative property of this operation GCD, and we have to discuss means we have to check whether the identity exists or not. If identity exists, inverse exists or not. If we want to make the identity, if we want to make identity to exist in this set, how to make it happen and stuff. I mean, we will just discuss like how this operation works on the set of integers in general. Okay, that's the aim of this question, to understand the set of integers, set of positive integers under this operation GCD. Or yeah. So first we have to prove the associativity property. So that is, we have to prove that for all ABC, I hope, yeah, ABC in Z plus, I need to check this GCD of A comma GCD B and C, whether this is equal to GCD of GCD AB comma C. Okay, I hope you all know the definition of GCD. Okay, so if something is a divisor of given element, it means, so we say that M is divisor of N if M divides N, and GCD between two elements is what we say maximum of all those D in N such that D divides M and D divides N. So this is divisor and we have to check which is maximum among the common divisors of these two elements. Okay, so I hope the definition is clear. And now we have to check this property. So let us start with this. So given that, so let us just give name. So let E be this GCD A of B and C, and let F be this GCD of GCD A, B and C. Okay, and we have to now check to prove that this E is equal to F. That's what essentially we have to prove. When we are saying we have to prove the associativity property for this given operation on the set of integers. Okay, so what do we need? If E is a GCD, since E is a GCD of this A comma GCD B and C, so this implies this E divides A and E divides GCD B comma C, right? That's what we have. And the moment, so this is there, and the moment I have E dividing GCD of B and C, so this will imply that E will divide B and E will divide C, right? Because GCD, this number, if I call this number to be P, so if, let me write this, if P is GCD B comma C, then what does this mean? P divides P and P divides C, right? I mean, that's how we start for the divisors. And since E is dividing this P and P divides B, this will imply that E divides B and E divides C. Okay? The division is transitive. Okay, so I have A dividing B, B dividing C, so A will divide C. That kind of argument we are giving here. So this implies what? That E divides A, E divides P, and E divides C. This is what I have got so far. So if that is the case, then E will also divide GCD of A comma B, right? And E is anyway dividing C. So this will imply that E will divide GCD of GCD AB and C. The properties of GCD. GCD is the greatest. So if two elements dividing, if a number divides two numbers B and C, the GCD will also divide this. This number E will also divide the GCD of those two numbers because it is greatest, and E is just number which is dividing that thing. Okay, so I hope you understand that. And and this is what my F is. That's how. So this is what F. So E divides F, and the moment I have this implies that F is greater than equal to E. Okay, and now similarly, if I start with the F was what? F was GCD of GCD AB and C. So this will imply that F divides GCD of AB and F divides C, and this will imply that F divides A and F divides B. The similar argument about if this GCD of AB is some Q, then since F divides that Q and Q divides A and B, this F will divide A and F will divide B. So F divides A, F divides B, and F divides C, and so this will imply that F divides A and F divides GCD of B and C. So this will imply that F divides GCD of A comma GCD B and C, and this was my E. So I get that F divides E, and then E is greater than equal to F. by this logic. And so I got that F is greater than equal to E greater than equal to F. So E has to be equal to F. And that's what I wanted to prove, that E is equal to F. And that's how we proved the associativity property of this operation. Any doubts here? No doubts. Good. Uh, cool. So since there are no doubts, so the associativity property is clear, I hope. So let us discuss about the identity. So what identity means here? So sorry. So what I want is to check. Let us discuss the identity of this operation. So what does identity mean? So identity is an element. So we want some A in n plus or z plus such that GCD of this A comma n must be equal to n, right? This is my operation for all n in this n plus. That's what some element being identity means. Or let us write E, as we have been using E as identity element. So I want some element E from a positive integers such that this E, when I take GCD with some given any integer n, and this is not how it should be written. So we want for all, wait, no, we want that such that for all w in n, sorry, n in n plus, this happens. Okay, that E, when I multiply with n, it again gives me back the same element. Okay, and note that this is commutative, that GCD of m comma n is equal to GCD of n and m. That's not a problem here. So I just want to check whether I mean, when we write the definition of identity, we also write it this way, that both the way it should satisfy. So identity element is such that it commutes with every element of the group. Okay, I mean, the group itself need not be abelian, but identity must commute with every other element. That's how it works. But yeah, so here we do not need to check this condition. Yeah, but we need to find some E. So if at all such E exists, so E star n, I want this to be GCD of n E comma n to be n. So this implies that GCD of E comma n is n for all n in natural numbers. This implies that E divides, sorry, this implies what? N divides E, right? And n divides n. N divides n is okay, but this implies that n divides E for all n in natural numbers. So do we have such number? So E is such that every element, every natural number divides that number E. So is this possible? Exactly. Other than E, no other element. Okay. What does that mean? Other than E, no, ma'am. Okay. You mean zero by that? See, any positive integer. So we are in n plus. So we are in n plus. Okay, I want positive numbers. Yeah, I mean, you are saying that only one divides E, but here you can take E square. Okay. Uh, what help would E square give us? So see, I want, so when I say something is the identity of my group under GCD, I started with this E and I arrived at this condition, and this condition must be satisfied by every natural number, every positive natural number or positive integer n. So this E is such that n divides E for all n. So give me any integer, positive integer, that integer will divide E. That's what that I mean, if the identity exists, it would satisfy this condition. But no such natural number exists, right? I mean, no natural number, positive natural number exists such that every element divide that. Every natural number divide that integer. That's not possible, right? So this is not possible. Because if identity exists, that identity is, I mean, when I take this binary operation of identity with some element from the group, it, yes, yes. So since identity does not exist, we can't talk about inverse, because how would you start with inverse if there is? So what is inverse? So if identity exists, then for A, I need B such that A in E operated on B gives me E, but there is no E to start with the question of inverse. So not possible. Okay, so identity. So therefore, this operation GCD operation does not have identity on the group of on the set of positive integers. Okay, and consequently, we cannot talk about the inverse. Okay, so yeah, as Pragya pointed out, we can't talk about inverse here. But we also note that the definition of GCD, so we now only considered positive integers, and we discussed whether on the set of positive integer it is, so binary condition is already given. We discussed whether the identity exists on the set of positive integers, and we saw that the identity is not there, and so we can't discuss about inverse. But note that uh, the definition of GCD makes sense on the set of integers. Okay, that is my Z, the end on the whole set of integers, positive, negative included. So in case if M and N are non-zero, both M non-zero, then GCD of Mn, I will just define it to be GCD of positive M and N like this. It won't change anything. That's how I am taking care of positive, or that's how I'm taking care of non-zero integers. But how to define GCD of M with zero? Because zero belongs to the set, right? So it is mod of M. Okay, for any M in Z, GCD of M with zero is just mod of M. If it is negative, we will consider. So GCD of -2 and 0 will be just 2. And why that is the case? Because see, 2 divides 2 and 2 also divides 0. Okay, so when we say something divides, so when we say A divides B, that means B is C into A for some C in N, right? N or Z, whatever we want to talk about, or whatever the given set is. So here I can say that 2 divides 0 since my 0 is 2 into 0 and my 2 into 0, and it makes sense since 0 is in Z. So this absolutely makes sense that GCD, when I'm defining it to be for 0 and M to be mod of M, it makes sense. Okay, and with this logic, GCD of 0 with 0 will again be 0, and I mean GCD of M with M is anyway M. GCD of 0 with 0 needs to be 0, and it's also mod 0 by this definition here, and it is 0. So it's well defined. It's completely well defined. It does not have any ambiguity when we discuss the GCD of any number with 0 and 0 with 0 itself. And then in that case, if I want to talk about identity, so if I want to talk about identity, what we needed was E in Z such that, so now we are discussing over the set of whole integers. So I want now E in Z. So now we are discussing on Z, okay? On Z set of integers. So now identity in Z such that E divides N for all N in N. But we know that, sorry. N divides E, not E divides N. N divides E. And what is that number? Note that N divides for all N in Z, N divides 0. We have this, right? For N, because 0 is 0 into N for all N in Z. So therefore we get that 0 is the identity element under GCD operation on Z, okay? Is this clear that this Z is now giving me the identity of my operation GCD on the set of integers? Okay, we saw on the set of positive integers, it was not possible, but on the set of integers, when I take the whole, when I take the set of integers, identity exists. Okay, so now we want to talk about inverse, whether it exists or not. If it exists, then whether it exists for every integer, and if not, then what are the integers where it exists. So so now since identity exists, we are now talking about the inverse in Z under the operations GCD. So now for A in Z, we want B in Z such that GCD of A and B, it needs to be identity. So I want this to be 0. So when is that possible? So note that if GCD exists, it is greater than equal to A and B. Sorry. If let me just say this. If A and B both are non-zero, then if GCD exists, it will be greater than equal to 1 always. Right? If A and B are non-zero, then if GCD, then we have defined GCD of A and B. and moment both of them are non-zero, GCD will be at least 1. Okay, because 1 would divide A and 1 would also divide B. Okay, so in that case, this GCD will at least be 1. So if I want to talk about inverse of some element such that GCD of AB giving me 0, then that only 0 is the possibility, because which will not be equal to 0. Therefore, if if I have even one of them, suppose if A is non-zero, then GCD of A with 0 will be mod A, that is non-zero. This is my first case. So therefore, so for any non-zero element, this is not possible, because it will be the mod of A, and since A is non-zero, mod of A will be non-zero, and we lose the inverse. So the hence the but for A is equal to 0, GCD of 0 and 0 is mod 0, as we have defined, and also that's how we define the GCD. Therefore, the only element for which, so the GCD greater than equal to 1 argument was not needed here, just the way we have defined the GCD for integers directly give us that for any non-zero integer, inverse won't exist. And the only element for which the inverse exists is 0 itself, the identity. Just a second. The identity. I hope this is clear now, that when we were talking about GCD operation on the set of positive integers, the identity element did not exist. But the moment we make our set bigger, we look at the set of integers which includes both positive, negative integers and 0. We got that 0 becomes the identity of the set under GCD operation. However, it does not give us inverse. Inverse does not exist for any non-zero integer. Only 0, the identity element, has the inverse under this operation, the GCD operation. Any doubts that how we showed that, not showed, how we observed that where where the inverse exists, where does not exist, and so on. Okay, you are great. Good. So now the next question, which is like follow-up question for this next one. So now they are saying that let m and n be positive integers, and then this zm plus zn defined like this: am plus bn, such that a comma b in z, this is subset of z, is a subgroup of z, then show that zm plus zn is z in GCD of this mn. I hope you know what zm and zn means. Okay, we have to show this, but I hope you know what is zm means: set of this set, all the multiples of m. And when we take this zm plus zn, it is it is actually sum of elements from the two sets. So in general, if addition is well defined, this for any set, this, if at all makes sense, it is A plus B such that A belongs to A and B belongs to B. But in this case, this A belongs to, with this A here, I'm writing AN, or let me write CD here. C plus D such that C belongs to A, D belongs to B. So here this C is actually my AM because ZM has elements of this kind, and D is set from element from this set B, which is in my case it is Zn, and elements there are of the form Bn for some B in Z. So that's what this Zm plus Zn is, and they are saying that it is subgroup of Z. Okay, so they are saying it is subgroup of Z, and we just have to show that this Zm. So you can check if you want that this is indeed subgroup of Z. Let me just write operation as well. Z comma plus. Okay, you can check that Zm plus Zn is subgroup of Z plus. Okay, so you can check this because we just discussed how to check whether some subgroup, I mean, for subgroup, you just have to check all the properties, whether they satisfy. Uh, so essentially, subgroup is group under the same operation, uh, which is subset of the given set, given group. And also one more thing, when we say something is a subgroup of a given group, the identity needs to be same. Okay. Otherwise, it does not make sense. The identity must be the same. I mean, it should inherit from the original group which we started with. Okay, so those are different things. But yeah, we need to show this, that this Zm plus Zn is actually equal to Z GCD of Mn. So how to show this? So we will start with the, so let me just write again. We have to show that this, so let, what, yeah, let D is equal to GCD of Mn, just for the sake of notations. This to show that Zm plus Zn, let me write this properly, Zm Zn is equal to Zd. Why I'm writing this like this and not, so this and this are different things, okay? This represent very different thing, and this represent, I mean, this here also, this is Zm, this is Zm, this is Zn. Yeah, yes. Okay, these two are different things. This is equivalence, sorry, equivalence class, and whereas this is just subgroup of Z, which is generated by the integer n. Okay, so please understand this. This when you write this, it is really wrong. Okay, so let me just write this as well. This Zm, this is Zn. This is not subscript. This is Z GCD Mn. Okay, so we have to prove this, and how to start. So note that if A divides B for any integer, so let A comma B belongs to n plus for the, because we are starting with m and n, positive integers. So if A and B belongs to n plus, and if A divides B, then note that this Z A will contain this ZB, or let me just write it. ZB will contain ZA. Because see, what does this mean? This implies that B is some M times A, right? And this is what? This is set of all set of all, what to write? XA such that X belongs to Z. And this is what? Set of all YB such that Y belongs to Z. But we already know that this B is of the form MA such that Y belongs to Z. So this is subset of this set because this becomes Ym into A such that Y belongs to Z. So it is collection of some multiples of my set, some multiples of A. So this inclusion is there. Let me use some other pen here. So this and this, this is inclusion here. So that's what I'm highlighting here. Okay. So I hope you understand this. So therefore, since D is a GCD, I have this D divides M and D divides N, right? So this will imply that Zm is contained in, sorry, contained in this ZD, and Zn is also contained in ZD. And this is not the correct, I mean, this directly does not actually gives us this, but the better way to do this would be, since D divides M and D divides N, this implies D divides AM plus Bn for all AB in N, and this will imply that in particular, and the moment I have this AM plus Bn would be some D times K for some K, and this will imply that this AM plus Bn belongs to ZD, and then this will imply that this is essentially expression for the elements from set Zm plus Zn. So this will imply that Zm plus Zn is contained in ZD. Here to here, I mean, you can directly say this, there is no harm, but also it's not that trivial that you can just conclude it. I mean, it is true because ZD is group, and so once it is group, it is closed under addition. So this actually makes sense, but the what we can say, in the background, the closure property is playing role here. Whereas here we can explicitly see that how given element from Zm plus Zn belongs to ZD. Okay, I hope you understand what I'm trying to say here. Here it is true, but in the background closure property is playing role to conclude this. But here in this argument which we are using here, we can explicitly see how the elements from Zm plus Zn belong to my set ZD. Okay. So now this inclusion is clear. Now the other way around. We have to show that we show that we need to show that this ZD is contained in Zm plus Zn. And understand that it is enough to show that this D belongs to Zm plus Zn. Because understand that this Zm plus Zn is a subgroup of Z. So it is closed under addition. That is, it satisfies the closure property. So the moment I have D in Zm plus Zn, um, all the multiples of D will be there. I hope that is clear. So it is enough if we show that this D belongs to Zm plus Zn. Okay. And how to show this now that D belongs to Zm plus Zn. So when I say that D belongs to Zm plus Zn, what does this? That is to show that D belongs to Zm plus Zn. That is we have to show. That is to show D is some Am plus Bn for some AB in Z. So how to prove this, that this exists? So you must have seen the property of GCD, that GCD is linear combination of the number whose GCD it is. Okay, so that's what essentially we need to prove here. In order to prove that ZD belongs to this Zm plus Zn, that is, we have to show that this. Okay, so how to prove that? Any ideas or guesses or any suggestion how to start? Now, suppose x be the smallest positive integer such that x is a linear combination of a and p, sorry, m and n. Okay, and we claim that x is actually this d. Okay, so what we are trying to say here, that when I have this set Zm plus Zn, the smallest positive integer in that set, which is linear combination of m and n, is actually GCD of elements m and n. That's what we are trying to claim here, and we will be proving. So first note that since x is a linear combination of bn, and since d is GCD mn, this implies d divides m and d divides n. So this implies that d divides am plus bn. So, and since x is this and we have this observation, I get that d divides x, right? This is clear. This is anywhere there. And then I get x is equal to am plus bn. X is am plus bn for some ab. And I have this property. I hope this is clear. Okay. Please someone tell me that this is not very difficult to understand. If there are any doubts, please let me know. But I assume you understood that why d divides x. And the moment I have d divides x and x is the smallest positive integer, d is a GCD, so it is again a positive integer. So, okay, it is clear, great. So I get that this x is greater than equal to d. I need to prove that x is equal to d. So far, I got that x is greater than equal to d. So we need to, the next step will prove by some assumption. Okay, suppose x is strictly greater than d, and we call it proof by contradiction. So we assume something which we do not want, and we arrive at the contradiction, something which does not make sense under given assumptions which are there, and then we conclude that okay, this is not possible, so the other case must be true. So that's what we are doing. We want x to be. So what does this mean? This means x is either d or x is greater than d. I want this. So I start with this here and arrive at some contradiction, arrive at something which is not making any sense under given setup which we have so far. So suppose x is greater than d. Okay. Then note that then x cannot divide the common divisor of m and n. Okay, because if x divides d and we already have d divides x, then I will get x is equal to d. But x is greater than d, we are assuming. So x cannot divide common divisors of m and n. And also common divisors of m and n are something uh, less than d because d is the greatest. So x does not divide m and x does not divide n simultaneously. Understand that. Okay, so we have x does not divide m or x does not divide n. Is this understandable? Because d is a common divisor and x is anyway greater than d. D is the GCD, that is greatest common divisor. And so anyway, x is greater than the greatest divisor. It cannot divide other divisors. And since it cannot divide other divisors, m and n being divisors of those numbers, x cannot divide m and x cannot divide n. Not and, x cannot divide m or x cannot divide n. Please understand this. And so without loss of generality, at least one of these should happen. At least x does not divide m or x does not divide n. It could be possible that x does not divide both of them, but it definitely does not divide one of them. Okay, so yeah, so without loss of generality, suppose x does not divide m. So what does that mean? So these imply we can write this, right? Mx plus r where 0 less than x. This is there, okay? This happens because see, x does not divide m. If x divide m, then m is equal to some x cube. But since x does not divide m, this r is non-zero and it is not equal to x as well. So this implies that r is less than x and r is what? It is m minus qx. So this is m minus q. What is x? X is this here. Okay, x is this here. So x is what? Am plus bn. So this is 1 minus q am plus Bn, and then R is less than X, which is also positive, and R is a linear combination of M and N. But this contradicts the choice of X, right? Since X was the least positive, which was linear combination of M and N. But the moment I have X does not divide M or X does not divide N, I get that there is some element R between 0 and X, so some positive integer smaller than X, which is linear combination of M and N. So it contradicts the choice of X, okay? And therefore, X does not divide M therefore, X greater than D is not possible. This is what we started. So this is what our first assumption was, which arrived at this statement, which does not make sense, which is not true in our setup, as X was the least, which was with least positive, which was linear combination of M and N both. So this is not possible. Therefore, the only option left is X is equal to D, and therefore this X is equal to D is equal to AM plus B, and this belongs to my set Zm plus Zn. And the moment I have D, I have Zd belongs to Zm plus Zn. Is this clear? That how this is giving me this? Because the moment I have this, since this is subgroup, any CD belongs to Zm plus Zn, right? Because this is what? CAM plus CBN. And this belongs here. Okay? And this is true for all C in Z. And once I have this implies that ZD is subset of Zm plus Zn. I hope this is clear to you. I mean, any doubts here? So we got that this ZD is this Zm plus Zn is ZD, and this D was indeed is indeed the GCD of this M and N. So any doubts here? No doubts. Great. Okay, so this was about GCD. Now, similarly, we can talk about LCM. Okay, so this next question, it talks about, let me just check. Mhm. Let us see how. Let again star be the binary operation on the set Z plus, that is all natural numbers greater than equal to 1, defined as LCM M comma N, that is least common multiple of M and N. Okay. And again, we have to show that this star is associative and discuss the identity and inverse of star on Z plus. So we again have to prove the associativity of this. That is to prove. So we first need to prove that LCM of A comma LCM BC is equal to LCM of LCM A comma B and C. This is what we need to prove. So let us just notation that E is equal to LCM A comma LCM B and C and FB LCM of AB and C. Okay, and so we have to show that this E is equal to F. That's what we need to show. I hope you know what multiple means. So multiple means that we say that C is multiple of A if C is A times B for some B in Z. Okay, and what we have to find is the least among such. So when we say that LCM of M comma N, so it is multiple of both M and N, and it is least among all such multiples. Okay, so the moment I have this, so here I hope you understand that it is least among the multiples of both M and N. Okay, so now what I have here, that E is my LCM of A and LCM B and C, right? So this imply what? What does this imply? So note that once I have this also imply that A divides C. Yes, exactly. So E divides all A, B, and C. So this E will divide, E is multiple of A, so E will divide. So what is that? No, sorry. Yes. So E will divide. No. A, B, C will divide A, right? Because E is a multiple of A. So E is some A into D. So A divides E. That's how it goes. So here A divides, not E divides ABC, ABC will divide E. That's how it is. So A will divide E and LCM of B and C will divide E. I hope you understand. Okay. Yeah, great. And now since LCM of B and C divides E, so this will imply that B divides E and C divides E. So I get that A divides E, B divides E, and C divides E. So this will imply that LCM of AB will also divide E and C is anyway dividing E. So this will give me LCM of AB, comma C will also divide E. And this was my F. So F divides E. So this gives me that F is greater than equal to E. Okay, and if you go with the same flow, similarly, you can show that E will divide F. You will arrive at the same conclusion that, that all the ABCs divide F, and then LCM of BC will divide F. Yes, exactly. We need to establish that F is equal to E. So once I have this, this will imply that E is greater than equal to F. And so from this and this, I get that E is equal to F, right? Because though these both statements hold E greater than equal to F and F greater than equal to E. So I get that E is equal to F, and this was my LCM of A, LCM of BC. I hope that's what I defined them as, yeah. And this was equal to LCM of LCM AB and C. Okay, so therefore associativity is done. Okay, any doubts in associativity? How so? To see this, that LCM of BC, what is LCM of B and C? That B is, if LCM of BC is some D, so D. So if LCM of B and C is D, just check. I mean, we are writing this. This looks that it is correct, but we also need to check. Okay, so what does this mean that D is some B, U, and D is some CV. And since it divides E, PU divides E, and CV divides E, this implies B divides C and C divides C. Yeah, I mean, yes, it makes sense. Okay, so that's how it goes. That it indeed B divides C and C divides C. Okay, I hope there's no problem here that if LCM divides some number, then each of those number divide LCM. Ugh. Okay, so now we want to talk about identity, and everything is happening in positive integers. Okay, this ABC are positive. So now we have to talk about, yeah. So now we have to talk about identity. And so what does identity means? We need some E in Z plus such that LCM of E with any number is again that same number for all M in Z plus. So what is your guess for this E? So this imply what? E divides M and M divides M, or what we say that M is equal to E least common multiple. M is equal to EK, and anyway, M is equal to 1 into M for some K in Z. So this imply that K divides M for all M in Z plus. That's what we want. So what is your guess for this E? that I want a number which divides every other number. 1, exactly. So therefore 1 divides m for all m in Z plus. So therefore my E is actually 1, because LCM of 1 with n is always n for all n, or m, since we are talking about m. Okay. So so now we have m, so therefore identity is 1. So we can talk about inverse, right? Since therefore identity exists on Z plus under LCM operation. Exactly. So as uh, Santosh pointed out, that since identity exists, we can talk about the existence of inverse for given element in the set. So since identity exists on Z plus under LCM, therefore LCM operation. So we can talk about inverse here. Okay, so what is your guess? So what does inverse means? So for given, or for m in Z plus, so see, we got the identity in Z plus itself. In earlier case, when we were talking about GCD, we did not have the existence of GCD in positive integers. We had to extend our set to Z plus, and we got that 0 was the identity in case of GCD. Okay. But here we got the identity in the set of positive integers itself, 1 being the identity on Z plus. Okay, and we are now talking about the inverse in Z plus itself. We can discuss about it on the whole Z later, but for now we are discussing the inverse, the existence of inverse in Z plus. Okay, so please understand the underlined set which we are talking about when we are looking for identity and inverse and everything. Okay, so for m in Z plus, we want n in Z plus such that LCM of m comma n is 1. Do we have this? Yes, we want that. We want n such that LCM of m and n will be 1. So I'm starting with my element m. So I want now n positive integers such that LCM when I take of m and n, it will be 1. So any guesses for this? So note that when we talk about LCM, we talk about multiples, right? Positive multiples. So it starts with m, 2m, 3m, so on. N is n, 2n, 3n, and so on. And we see which is the common among them and least. And that's how I get my LCM. So when we talk about LCM of two integer, it is at least greater than equal to this m and n, right? So LCM of m and n, it greater than equal to m, or it is greater than equal to n. Is this clear? So if equal to m and n, and n, it's not or, it's and n. Yes, it is and n. So if m not equal to 1, if at least, so if m not equal to 1, then LCM of m with n will be greater than equal to 1 for all n in n plus, right? That's what we saw. It will be greater than equal to both. Because even if it is n, yes, it is greater than equal to both. Because if the LCM is n, it would match with one of the multiple of m here, maybe something here, some kn, and it is this kn is anyway greater than m. This kn is greater than equal to m, and n is anyway greater than equal to n. So I hope you understand what I'm trying to say here. That it is greater than both m and n. Uh, so if it is some kn here, km is some kn, that is my LCM. So this is greater than m and this is greater than equal to n. So it is greater than equal to both m and n. So this LCM, if m is not equal to 1, this LCM will be greater than equal to m, which is strictly greater than 1 in my case. So therefore, LCM of m and n is not equal to 1 for all m not equal to m positive, because we're looking at exactly. So as Santosh said that if m and m are not equal to 1, LCM will always be greater than equal to 1, because at least one of them is greater than equal to 1. Not greater than equal to, greater than 1. Okay, so LCM, if I want to calculate it for some number with some other number where one of them is not equal to 1, the LCM would always be greater than 1. Okay, so therefore, only possible case is LCM of 1 with 1, and that would give me 1. Okay, so therefore, if m is equal to 1, LCM of 1 and 1 becomes 1. So actually we should have discussed, if m is equal to 1, then LCM of 1 and 1 is 1. But if m is not equal to 1, I get this. Okay, so the only two cases we had. And I got that LCM of 1 with 1 is 1. Any doubts here? So inverse exists only for the identity element, right? My 1 was the identity under this LCM on Z plus. So now what about Z on Z, the whole integers, set of all integers? Because this we discuss on Z plus, right? Now for Z, what is your guess? So see, identity is there. Identity is there even on Z plus. And now I'm discussing on bigger set. So identity will continue to be identity in bigger set as well. Otherwise, it won't make sense. Okay, so now what I want to check here is whether inverse makes sense on the bigger set or not. I hope you understood what I'm trying to say here. First of all, let us see how LCM is defined. So for mn in Z and m and n non-zero both, let me just write explicitly. LCM of m and n is LCM of mod m mod n. That's how I define the LCM. But for one of them 0, the LCM of 0 with m and LCM of it just 0, because see, 0 is 0 times m or 0 times k for all k in z. And since I'm talking about whole z, this 0 is also m times 0, right? So this 0, so when see, I mean, when I was looking at the multiples, with 0 and m, I mean, when I'm talking about 0, I'm also including 0 as a multiple of m in that case. So 0, this is just notation for I mean, something we define to make sense. Okay, so 0 and m, so 0 is also multiple of m when I multiply m by 0. So that's why LCM of 0 and m, I define it to be 0 again. Yeah. So this is like common multiple of both 0 and m. So now I want to talk about the inverse, whether it makes sense here or not. So on bigger set, what would be the inverse? So for, if I choose for m in z, what I want LCM of, wait, does this make sense? Because if this is how I'm defining, yes, it makes sense, right? Because then LCM of 0 and 1 would be 0, and the identity still holds. For positive, it is anyway mod m plus mod n and 1, so that's okay. So identity still holds here, that's what I'm saying. So for positive integers, for negative integers, it was not a problem because we anyway were taking LCM of m and n to be LCM of mod m mod n. And when I was taking LCM of, wait, do we need to have mod m and mod n here? No, right? Because 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 if I take mod m and mod n, then LCM of mod m with, see, here this, if I define this to be this, then LCM of, for just example, -5 and 1 would be what? LCM of mod -5 comma 1, and this would be LCM of 5 comma 1, which is 5. And this, I mean, this is not what we call identity as. So I think for LCM, we have to take -5 to be just -5. And then if that's the case, then same needs to be true for GCD as well. Because, where is it? Did I define it anywhere? Mm. Yes, GCD. But if that's the case, so since here we are defining GCD of a comma 0 to be mod a, then in that case GCD of -a comma 0 will also be mod -a, which will be a, right? So it's still, there is some problem. Let's see. Do we really need to have that mod there in order to define GCDs and LCMs? I don't think so. But when we say greatest, it has to be positive, because if -5 divides some integer, 5 also divides that integer by the definition of division in Z. And then 5 by default becomes the greatest among those common divisors. So GCD has to be positive in that case. And similarly, common multiples, I think it would be the same. Okay, so I think we are defining GCD then LCM to be positive integers always, or non-negative, since we are including 0 as well. Yeah, so if I am also taking this LCM of, so if M is in Z such that M is non-zero, then LCM of M with N will be, I want this to be N such that GCD of Mn to be 1. Sorry, LCM of Mn to be 1. But again, it will be greater than equal to M and greater than equal to N. And so therefore LCM of M. So therefore for non-zero M in Z, inverse does not exist. The same argument works. Even for negative cases, the same argument would work. Because anyway, when we were talking about positive integers, we had identity there and we saw that for positive integers, inverse does not exist. And similar argument works here because we saw LCM is greater than equal to mod of both M and N when we are taking LCMs. So, and for 0, if my M is 0, LCM of 0 and M, I am taking it to be 0, but this is not equal to 1, which is my identity, right? So therefore, but for M is equal to -1, LCM of -1 and 1 would be 1, right? Or it will be -1. It will be -1, right? Least common multiple. So if I take this set multiples, if I take something generated by -1, it is the same set, right? So -1z is just z, if you see, and the least common does not make sense in that case. So if we are considering only positive, then minus LCM of -1 and 1 would be 1. And in that case, therefore, the only possible elements who has, but see, if inverse exists, in this case, this LCM of -1 and -1 would also be 1, right? If we are looking at the positive multiples. So, I mean, this, if you look at the uniqueness of inverses in this case, then this does not have the unique inverse if we look at it that way. So the possible elements who are invertible are 1 and -1. So note that inverse from this, inverse need not be unique. Okay. Uh, but when we talk something is a group with particular identity, and if inverse exists, it is unique. But in such cases where we are talking about the inverses, these are, so this is what, so if at all inverse exists, it will exist for -1 and 1, only two possibilities, and not the rest. Okay, I hope it did not become too abstract for now, but are there any doubts here? It's clear, right? I mean, you understood what I was trying to say when I said about inverse not being unique and the way the LCM and everything is defined here. Okay, so yeah, I hope this was clear. And you can now, I mean, you can do this exercise for yourself. This may be question 5 or what. I mean, it's there in your assignment sheet as well. That question, what question we are discussing? I think it was question 5. It is question 5 that prove that, I'm just writing shorthand, prove that this Zm intersection Zn containing Z is a subgroup, and Zm intersection Zn is Z LCM of, sorry, M and N. Okay, you can prove this. Try to prove this the similar way we did for GCD in that. Okay, and if there are any doubts, ask in the discussion forum. And yes, so we are anyway over time. So if you have any questions, please ask, or we can end the session here. And if you have any doubts, please, okay, ask those in the discussion forum. Okay, see you next week, same time. Bye.